All right. Hi, everyone. Welcome to the online causal inference seminar. So today we have a talk by Thomas Richardson from the University of Washington on single world intervention graphs, a simple framework for unifying graphs and conditional outcomes with applications to mediation analysis. And we have a special guest in the Q&A. So Jamie Robbins from Harvard will be taking your questions, and he might also answer some of the questions as well. And after this talk, we will also have a discussion by Matt Stensrud from EPFL. So yeah, I hope you all enjoyed the talk. Please use the Q&A to ask questions, and I will forward it to Ying, who will further explain.
Yeah, please use the button Q&A in the window to submit your questions, and James or Thomas will answer your questions. And I'll give the stage to Thomas.
Okay, share my screen. Okay, is that good? Can you see my screen?
Yes, great.
Great. So thank you for coming to this talk. I hope those of you, at least in the US, I hope you had a relaxing Thanksgiving. So to give you this, I should say this is joint work that I'm with Jamie Robbins and more recently Ilya Spitzer. And just to give you an overview of this, I'm going to first talk about SWIGs, which are a way of relating causal graphs and counterfactuals via a simple node splitting operation. I'll go through some simple examples, give you a general procedure, and then I'll go through some examples, simplest being adjustment for confounding. Then I'll show a way that we can reformulate Pearl's do calculus in terms of potential outcomes, something we call the PO calculus. I'll illustrate the front door criterion via the PO calculus and give you some examples of using this framework to think about sequentially randomized experiments or time-dependent confounding. And then, time permitting, if it does, I'll talk a little bit about mediation and separable direct effects and contrast with other approaches. But before I do, I just want to give you a very high-level sort of cartoon overview. So I should say what I really appreciate the work that has gone into setting up this online causal inference seminar. I think it's one of several efforts that has really started to make causal inference as a sort of cross-disciplinary field really solidifying. But one thing that you'll have noticed from the talks is that there are some talks where people say I'm going to be doing things using causal graphs, and there are other talks where people say I'm going to be doing things using potential outcomes. And I sort of think about these in some sense as different worlds or countries. So, you know, there's causal graphania, and in that world, you know, we wake up in the morning, the first thing that we see is a DAG representing the pre-intervention world. And then, you know, and then we then think about what would happen if we were to intervene, and that's by cutting edges on the graph. And then there's sort of potential outcome land. And in that potential outcome land, people wake up in the morning and the first thing they sort of conceptually see is a distribution over potential outcomes, which is sort of what would happen to individuals under if they were assigned to treatment or control. And then sort of the other way around from causal graphania, they then, people in potential outcome land then build the world of passive observation from that potential outcome distribution. And these are just two different ways of approaching things. Those are like two different languages. And the goal of this talk, in a certain sense, is to build a bridge that allows us to join those two worlds together. And one thing about a bridge is that a bridge can be crossed in two directions. So you can sort of start on this side of the bridge and cross this way, and that's basically what I'll be doing in this talk. But this bridge, because it's a bridge, you can also start in this world, and then you know, if you understand potential outcomes, you can then use that as a way of building graphs. Okay, on with the talk. So the graphical approach to causality, the sort of very highest level, we draw a graph, and we have a convention when we're interpreting the graph causally, whereby we say that you have to include any confounding variables on the on the graph. And so the convention is if I don't show you a confounding variable, then there's an assumption that there is no confounding variable. And this approach goes back to path diagrams introduced by Wright, and it's been was extended greatly by work by Spirtes, and Pearl, and many other authors subsequently. In the graphical approach, we have a factorization associated with the graph, and in the absence of confounding, the causal model, because we're assuming there's no confounding, it asserts that the distribution resulting from intervening on X is the same thing as the conditional distribution. And this is here, I'm writing this also in terms of potential outcomes. This is the way it will be written in terms of potential outcomes. And so things like the average causal effect of X on Y is identified under this model. So the question is, how does this relate to the graph, how does this relate to the non-graphical approach? So to describe that here, so in the potential outcome approach, the absence of confounding, weak ignorability, would correspond to these two independencies. That treatment is independent of the potential outcome under control. Here I'm using X sub 0 as a shorthand for X equals 0. And the potential outcome, the treatment is independent of the potential outcome under treatment. So this is the way that in potential outcome land, people think about the absence of confounding, and this is the graphical way of doing it. And then, conversely, confounding in potential outcome land means that one of these independencies doesn't hold, one or more. So the question is, how do we relate these two approaches? And the thing which is particularly interesting is that the potential outcome, people in potential outcome land are thinking about representing the absence of confounding in terms of an independence. And those of you that are familiar with graphs will know that graphs, one of the great strengths of graphs is that they're a way of reasoning about independence and conditional independence. And so the question might come, well, okay, great. So that we've got a causal graph, and we've got the absence of confounding is being represented by this independent statement. So surely there must be a way to read off this independent statement from the graph. But there's a sort of obvious problem that we have here, which is it doesn't matter how long you stare at this graph, there are no potential outcomes on that graph. So you're never going to be able to read these things off. Okay, they just don't appear on that graph. And so how are we going to address that? Well, we're going to address that by introducing an operation that allows us to change this graph in such a way that it will introduce potential outcomes, and then we'll be able to read off these independencies from the graph. So what are we going to do? We're going to take this original graph representing the sort of pre-intervention, the world in the absence of an intervention, and now we're going to split this X variable into two pieces, a random piece and a fixed piece. And then everything that's sort of downstream of the fixed piece is going to be labeled as a potential outcome, with the label being given by the value that we fix X to. Okay, so for now, I just want you to think about this as a sort of as a symbolic graphical operation. I'll give you some intuition for it shortly and sort of give you allow you to see more of the theory. But for now, just think about it. Here's this trick. I could split X, and I could I'll have a random X, a fixed piece, and then everything downstream of that will be labeled as a potential outcome. So now, even if you don't have the full details of deseparation on the top of your head, you can think, well, I've got a node X here, and I've got this other node here, and there's no path between this guy and this guy. There are no edges linking this to this. So therefore, we can read off the independence that X is independent of Y of X equals 0. Okay? Great. But I need to also, if I'm going to think about this as representing a joint distribution, I need to tell you, well, what is the joint distribution that it represents? I've told you that it's going to be a joint over this random X and this potential outcome, and their independence, so it's going to factorize. But now I need to also tell you what is this distribution going to correspond to? And I'm going to obtain that from the original observed distribution by plugging in X equals 0 into this term in the factorization of the original observed distribution, which will then give me the new distribution that I need over this potential outcome. And so at a high level, this new graph is doing two things. It's got a factorization. Factorizes is representing a joint over these two random variables, x and y of x equals 0. It's telling us that that joint distribution factorizes. And then we've got a rule that allows us to obtain this potential outcome distribution from the original graph by just plugging in x equals 0 into this term in the factorization associated with the DAG. And so we call this the first assumption factorization with respect to this new graph, and the second, the linking assumption, modularity. Okay, and you might say, well, that was great. Could we do that with another value? And of course we could. We could split and set fix x to x equals 1, and that would give us this graph, and then we'd read off the independence of x and y of x equals 1, and we would get another factorization, the obvious the same factorization except with the potential outcome y of x equals 1. And then if you ask, well, where does the Maxwell distribution over y of x equals 1 come from? Yes, you guessed it, it comes from this conditional piece up here, but now we're conditioning on x equals 1. Okay, so now I've built for you, you came to me with one graph and one joint distribution. I've now built for you two graphs, one with x equals 1 and one with x equals 0, representing two marginals over x and y of x equals 1 and x and y of x equals 0. Okay, so g of x0, that's the first new graph that we built. G of x1, that's the second new graph that we built. And the key point here is that under no confounding, these two marginals are identified from the original joint distribution that we had. Okay. In contrast, one way that we might have tried to combine graphs and potential outcomes might be to just say, if in potential outcome land they're interested in these potential outcomes, well, why don't I just build a big graph that contains all of these variables in one go? And that's very tempting to do, but there's an issue, which is then you're building a graph for a joint distribution that is not identified from the original observed data. Okay? So it's a key point that we constructed two graphs here because we want to be building graphs for things that are identified from the original observed data. Okay? And connected to that, if we were to construct a graph that had all three of these variables on, then sort of from the way that graphs work in terms of combining independencies, if our graph represented these two marginal independencies, then we'd also sort of be forced to represent this joint strong ignorability condition. And you might think to yourself, well, is that really that much of a concession? Because, often the situations where we'd be willing to make these assumptions are situations where we'd also be willing to make this assumption, like, for example, that X was randomized. And that's a very reasonable point. But the issue is that when we start thinking about situations with more variables, with more complicated graphs, if we start, we very quickly start the graph starts introducing additional assumptions, and those assumptions are not testable via any randomized experiment, and they moreover lead to identification results. And those identification results are also not testable via any randomized experiment. Okay.
Thomas, can you hear me?
I can.
Okay. Somebody asked the question, being a counterfactualist, this weird thing you were saying about modularity or whatever you called it, what's its relationship to consistency?
So I think essentially the short answer to that is that from a counterfactualist perspective, you could derive the modularity assumption via consistency.
Right.
That would be my.
So I would say, well, I would just say that whoever asked it, you're right. That the way I would have talked as a counterfactualist is I would have derived it in one step from consistency. But maybe it would be useful if you did that, Thomas. But
okay, maybe we can come back to that.
Okay.
So there are some other questions coming up. So there's a question here about what's the relationship between this approach and twin networks? And essentially, maybe we can come back to that at the end. But one of the issue of twin networks is that with twin networks, you are essentially imposing these stronger independence assumptions. I don't know whether, yeah, I don't know whether that question is still outstanding, whether it got answered, but seems to have gone. Okay. Yeah, so the key point is the reason why these things are called single world intervention graphs is that we're going to have that the graphs they don't represent joint distributions over all the potential outcomes, they represent joint distributions over potential outcomes that are compatible with a single set of interventions. Okay, so I constructed two graphs for you for different values of the fixed node. And you might say to yourself, well, you know, that seems like, what happens if X takes 10 states? Do I really need 10 different graphs? And of course, we can represent all of the graphs for different levels of X via a single template. But the reason I go through introducing this fixed, you know, two graphs at the beginning is because if we look at this, it's important to understand that this is essentially a graph value function, where you come to me with a particular value of little x that's corresponding to our intervention, and then, you know, then I can plug that into this template, and that then constructs for me a graph. So if I stick in x equals 0, that gives me the first graph, x equals 1 gives me the second graph, and so on. Okay? So this is a graph valued function, not a graph. It's a black box where I stick in particular values of x, and then it gives me this, gives me out a particular instantiation. Okay, so this, you know, the first instantiation was this one, second instantiation was that one. Okay, so how could we, so to give you a little bit of intuition about this splitting operation, so you could think, what am I doing in the splitting operation? I'm claiming that I'm sort of conceptually thinking about a world where I can both see the natural value of x, and I can also see someone's potential outcome. And so you might think to yourself, well, how could that arise? Because it seems quite strange. For example, how could it be the case that I know someone would naturally take treatment, but then also observe their potential outcome under control? So in order to do that, I'm going to give you this thought experiment. And the thought experiment is, well, how could I know that someone would take treatment, but then also see what would happen to them if they didn't take treatment? So this is a notion that might seem quite strange to you, especially if you're coming from sort of the world of the do calculus. But so here's the thought. The thought is, supposing we had an experiment where we observe a patient in real time, and then at the moment where they're on TikTok, or we're sort of following them on their in-home cameras, and at the moment where they observe the drug, we observe that they swallow the drug, we instantly intervene, and then we administer an emetic that causes the pill to be regurgitated. So the idea is that we're monitoring someone continuously. We can see the moment at which they decided to take the drug, and then at that instant we're then going to intervene. So in that way, we both get to see what this endogenous variable x, so what they would have chosen in the absence of intervention, but also we can sort of swoop in and intervene just at that instant in order to prevent their choice having any downstream causal implications. Okay. And because we're supposing that, you know, conceptually the emetic has no side effects, we're then able to observe the patient's outcome under control. Okay, so let me just give you a slightly more complicated example. So supposing I've now got this graph, I've got two treatments A and B, and suppose we want to ask the question, is the potential outcome Y of AB independent of B of A given Z of A and A? So here now on the right, I've constructed the SWIG corresponding to that. I split A, I split B. Everything downstream of A has been labeled with an A. Everything downstream of B has been labeled with a B. We did the splits before we did that labeling. And then now, you know, by D-separation, we can then see, yep, Y of AB is D-separated from B of A given Z of A and A. In fact, you know, we wouldn't need to condition on A here. We would still have this independence holding But I'm conditioning on a because, and this sort of relates a little bit to the question that was raised in the chat about twin networks. If you attack this problem with twin networks, there's a simple there appears to be a deconnecting path, which suggests from which it's easy to make an invalid inference if you're not careful. So that's so essentially a simple way of saying that is that whilst deseparation in a twin network always implies independence, the presence of a deconnecting path in a twin network does not always imply that there exists a joint distribution where we have dependence. So deseparation is not complete for twin networks because of deterministic relationships. Okay, so let me tell you a little bit more about this scheme. You probably have got the idea already, but I'll just give you 2 slides to state the general form of it. You're going to come to me with a graph, and then there are going to be a set of nodes that I'm going to split in order to describe a joint distribution over potential outcomes where I intervened on those variables. And when I do that splitting, the fixed half, I'm going to create a random part and a fixed part. The random part will inherit all the children. The fixed part will inherit all the parents. And then I'm going to relabel the descendants of the fixed node. So this slide is a bit busy, but basically here's the graph after I did all my splits. And then everything that's downstream of this fixed node is then getting labeled with the little a. Okay, and so here to summarize, adding counterfactual distributions to DAGs, we start with our original graph, we construct the counterfactual distribution, and then under minimal labeling, so I should be clear, as you can see, for example, in this graph here, although I split A and B, not every variable in the new graph is labeled with A and B. So although I'm going to call this graph here G of A, B, not every variable in that graph has got an A and a B in it. Okay, and then factorization is we're going to assume that the new joint distribution factors according to the new graph that we've constructed. And the modularity assumption is going to be that we're going to assume that the distribution of a variable in the new graph conditioned on any non-fixed parents, any remaining random parents it has, is just the conditional density associated with Y in the original graph after substituting the fixed value for any parents that have been split. And the consequence is that if the original distribution over all variables is observed, then the new distribution over all the potential outcomes is identified. Okay, and then, so, if you've come across graphs, you'll be aware there's this very powerful notion of deseparation that allows us to read off conditional independence from graphs. And that can be applied to SWIGs directly. There's just one little caveat, which is now the new graph I've constructed has these fixed nodes in it. And so I have to tell you how those are going to interact with the deseparation criterion. And I do that in 2 parts. So the first part is if a red node occurs on a path as a non-endpoint, so if it occurs somewhere along a path, then it's always blocked. Okay? I'll say in a moment, a path on which one endpoint is a red or fixed node can deconnect that node to a random node if it satisfies the usual conditions on colliders and non-colliders. And so I'll give you the interpretation of that in a moment. But first, just to consider paths that start on a random node and end on a random node, they will have the usual interpretation, which is that if I've got a set of random nodes and those are deseparated from some other set of random nodes given some third set of random nodes in this new graph, then I will get the corresponding conditional independence holding in the joint distribution over these potential outcomes. And I should also make a note here that this model that we're getting for the potential outcomes corresponds to a model introduced in Rubin's 1986 called the finest fully randomized causal interval structured tree graph. Okay, so let's talk about apply this to a simple problem of adjustment for confounding. So supposing that I've got this graph on the left, then as you may graphical people immediately see, I can control for confounding. That L is sufficient to control for confounding. But but in the potential outcome land, we would think about this in terms of conditional ignorability. If I split x into these two parts here, now I can read off from this graph that the potential outcome y of x is independent of x given L, which I can see via D separation. So I can read this off, and then I can then obtain identification via just law of total probability, followed by using the independence that I had, and then followed by consistency. Okay, and then I can, if somebody said, well, but wait a second, suppose that there was a potential, supposing there was a potential hidden cause between L and X, hidden common cause between L and X, then we can split on X and we can see that the D separation fact is not changed. So we're going to continue to get this conditional ignorability. Or if the hidden common cause was between L and Y, then we would get the same conditional ignorability and the same identification. But if we had both types of hidden variable present, then we would then lose this conditional ignorability. Okay, so something that you are also probably aware of is that Pearl formulated this do calculus for reasoning about intervention distributions in DAGs. And so here's where we're going to be able to use D separation with fixed nodes. So I remember I only so far told you about how to interpret deconnection or D separation with paths on which both ends of the path were random. So now, supposing I've got a fixed node and it's D separated from some set of random nodes given some third set of random nodes, then that will imply that the conditional distribution of B given C in a world where I intervene on A and D is unaffected by the specific value to which I fix D to. So it's saying that the conditional distribution of B given C when I intervene to set A to A tilde and D to D is the same as the conditional distribution I would get if I fix A to A tilde and D to D prime. So the conditional distribution of B given C after intervening on A and D does not depend on the value assigned to D. Okay, so how does this connect to, so given this idea, this gives us tools that allow us to reformulate the do calculus. So just to quickly review that, the do calculus, Pearl gave us, formulated 3 rules. One was about when we could remove observations. So I've written it in terms of do and in terms of potential outcomes, whichever you're most most comfortable with. The idea is basically I see W and intervene on X, and then the question is whether or not also seeing Z changes this distribution. The second rule allowed you to interchange observation and intervention. So on the left we have we see Z and see W but intervene on X. And on the right we see W but we intervene on both Z and X. In potential outcome terms, express it like that. And then the third rule talked about when you could remove an intervention. When we see W intervene on Z and intervene on X, when is it the case that intervening on Z does nothing? Okay, and Pearl gave graphical rules under which you could do each of these operations. The rule especially, these rules involve 3 different graphs, but especially the third rule, the graph is quite complicated. I'm not going to go over it here, but if people are interested in Q&A, we can maybe talk about it. So this can be reformulated in a rather simpler way using counterfactual versions of Pearl's rules in terms of SWIGs. So the first rule is just D separation, just says, okay, I construct my SWIG and I look to see if I have D separation. If I have D separation, then I can, not whether or not I condition on Z has no effect on the conditional distribution. The second rule says that if Y of XZ is D separated from Z of XZ given W of XZ, so I construct the graph where I intervene on X and Z, and if I have this deseparation, then I can go from, then it doesn't matter. Intervening on Z is the same thing as not intervening on Z, but observing it. This actually, you can also, in some sense, can also be thought of as an instance of using deseparation and consistency. And then the third rule gets simplified quite a lot. It just says if Z has no directed path to Y of XZ in G of XZ, so in a world where I intervene on X and Z, if there's no directed path from the fixed node Z to Y of XZ, then these two distributions are the same. Then the distribution in the world where I intervene on X and Z, the distribution for Y is the same as the distribution for Y when I don't intervene on Z. Okay, so this still may look a little busy to you because we've, I'm intervening on X all the way through, following the way that Pearl set it up. I'm intervening on X, but for the moment, supposing we just leave that out because it's just sort of context. In some sense, it's just starting off. We're doing everything here is in a context where we've already intervened on X. So supposing I drop that, then essentially we could rewrite these rules if I drop the intervention on X. So the first rule is just deseparation. The second rule corresponds to this, which is sort of generalized ignorability. And then the third rule is just if Z has no directed path to Y of Z, then these two things are the same. So this is sort of deseparation, ignorability, and causal irrelevance. Right? If there's no path from Z to Y, then intervening on Z has no effect on the distribution of Y. So we've sort of distilled the do calculus down to just these three things: deseparation, ignorability, and interventions only affect causal descendants. So here, just to show you an example of this, so this is the sort of famous front door graph where the task is to, that we don't observe U, and the task is to get the distribution over Y when we intervene on A. And so, just to show you how this could be done using the Poe calculus, we just use the law of total probability, we can rewrite this in this way. And then by looking at the graph that we've got over here, we can see that A is deseparated from M of A marginally. So therefore, we can replace this term with this term. That's rule 2 that's been used. And then we can then see that if we intervene on both A and M, we can see that Y of AM is now deseparated from M of A. So consequently, this term can be replaced by this term. And then now we can see that in this graph, there's this fixed node A is no longer an ancestor of Y of AM. So we can drop the A here and we get to this expression. And then now we pull out P of M given A to the front. We use the law of total probability again on this. And then finally, looking at this graph we've got down here, we can then see that Y of M is deseparated from M given A. So therefore, this term here can be replaced by this term here. And I don't have time to present this here, but this, the ID algorithm developed by Jintian and proved to be complete by Ilya Spitzer and Pearl and Wang and Valtorta, that can also be reformulated in terms of these SWIG operations. Okay, so let me also show you quickly doing this with sequentially randomized experiments. So supposing I'm in this world that I sometimes think of as the sort of Jamie Robbins world, where I've got a treatment and then I've got a response, and then I've got another treatment that's assigned randomly conditioned on the past, observed past, and then I've got a final response. That there's potential confounding between these two responses. So B is a time varying confounder, D is the final response, A and C are treatments. And we want to know what would result if we had done a completely randomized experiment where both A and C were randomized rather than C being randomly assigned conditional on A and B. Then, this could be derived via the co-calculus or the ID algorithm, but Robin's 86, the G formula, says that if we could get these two independencies to hold, if A is independent of D of AC and C of A is independent of D of AC, given B of A and A, then this intervention distribution can be identified by the expression on the right. And so the question is, do these independencies hold? And we could just split, and we can then read off, yep, A is obviously D separated from D of AC, and C of A is D separated from D of AC, conditional on B of A and A. Here we have to remember that this is a fixed node, so it cannot rise as a non-endpoint on any path. And B of A we're conditioning on, so it blocks any path from C of A to D of AC, either this one or this one. So we can read off these two independencies, and we can see that Robin's G formula is going to identify this double intervention. We could think about slightly more challenging examples. So for instance, suppose that we had confounding between A and B and confounding between B and D, but then there was no edge from B to D. Then again, we can construct the SWIG over here on the right. You can check that these D separations, D separations in the graph continue to hold. So we're going to get these independencies. So the identification result will continue to hold in this particular case. But we can also see that had there been an edge from B to D, then we would not have got this independence, because in that circumstance, A would become D connected to D of AC by a path A, H1, B of A, and then the edge from B to D. So we would lose this identification result. Okay, so summary so far, SWIGs provide a simple way to unify graphs and counterfactuals via node splitting. The approach works by linking a factorization associated with the two graphs. The new graph represents a counterfactual distribution identified from the distribution on the original DAG, and that provides a language that allows counterfactual and graphical people to communicate. So there are some things I haven't covered. So we can have an extended version of the idea algorithm via a sort of fixing operation that corresponds to splitting and marginalization. SWIGs can also combine information on the absence of individual and population level direct effects. And they also, it permits formulation of models where interventions on only some variables are well defined. So for example, the front door graph example I went through, we might want to see whether that identification result could be obtained without intervening on M, and it can be, even though the derivation that I showed did intervene on M. Okay, so let me talk just for a little bit about interventional mediation. This is the second part of the talk. And so here I'm going to give you a fairly new way to think about mediation and direct effects in terms of what I'm calling separable direct effects. So direct effects of mediation, here's my graph. X is initial treatment, M is a mediator that's a mediating variable of interest, Y is the final outcome. We want to allow for the possibility that there's confounding between M and Y. We're sort of thinking of X as being randomized. Okay, so in the linear case, if we had a linear model, a linear structural equation model, we could write this down. We'd have coefficients associated with each edge. And then, where we assume that the error terms are all uncorrelated. And then, that this edge coefficient alpha will be the effect on M of a 1 unit change in X. And then the effect on Y of a 1 unit change in X would have two components, a direct component gamma and an indirect component alpha beta. The question is, how do we generalize that story to the non-parametric setting? So here, I'm going to think about a thought experiment that was essentially originally introduced by Pearl, but it wasn't the way that Pearl decided to ultimately think about direct effects. He did it in a different way. So supposing that we've got X is smoking status, M is hypertension, blood pressure, and Y is myocardial infarction, and suppose that smoking, we can decompose smoking into two things: nicotine exposure and other chemical components of cigarettes. Okay? And let's suppose for the moment, just suspend disbelief and suppose that that this graph on the right represents the way that things operate, so that nicotine only influences, only has an impact on heart attack through blood pressure, but there are other components of smoking that also have an impact on heart attack. Okay, so this is nicotine, and this is the other components of smoking. Okay, and now suppose we've got well-defined interventions. So in particular, you could imagine that I could create cigarettes that say have got the nicotine taken out, but they've got the other chemicals present in cigarettes are still there. Then we could think about a direct effect. We could think about the effect of, say, people smoking these cigarettes that have got nicotine taken out, and the effect of that versus not smoking at all. So there we're thinking about holding that people are not getting any nicotine, but the people that are smoking the nicotine-free cigarettes are still getting the other components, but they're not getting the nicotine, and the control group's getting neither. Okay. Or we could do it the other way around. We could think about the effect of getting a nicotine-free cigarettes versus sort of getting the smoking a regular cigarette. So in that particular case, we're holding we are holding this fixed at 1, but we're now looking at the effect of getting nicotine or not getting nicotine. Okay. So we could also reformulate this. Instead of thinking about X and the interventions on N and O, we could think about it we could re-express both these interventions in the case where if X is 1, both of these things are 1. If X is 0, both of these things are 0. So we can reformulate those interventions that I described in terms of X and N and X and O in terms of just N and O directly. Okay, and so then I can write my direct effect and my indirect effect in terms of just N and O. And then, moreover, if I then add together the indirect effect and direct effect, I'm then getting the contrast. I'm getting the difference between X equals 1, which corresponds to N equals 1 and O equals 1, versus X equals 0, which corresponds to N equals 0 and O equals 0. So here, these red edges are indicating the fact we've got a deterministic relationship. So when X is equal to 1, so when you're assigned to smoking, you get both nicotine and the other chemicals. When X is 0, you're not smoking at all, you're getting neither of these. Okay, so now I'm going to just think about identification, and I'm going to think about 3 data sets. So the first data set consists of the original observed data from the trial in which X is randomized. Second data set consists of a putative, we haven't actually done this, but a putative 4-arm NO randomized trial. The data in each arm NO. So we can think about randomly assigning people to the 4 different levels of N and O, in which case we'll get to observe M of NO and Y of NO. And then the third data set is going to consist of supposing that somebody accidentally lost the 2 of the 4 arms here, the 2 arms where N and O took different values. So we only have the arms where N equals O. So either N equals O equals 1 or N equals O equals 0. So in the original data, X was equal to N is equal to O. You have these red equalities. And so among people with X equals X, we observe N equals O equals X. So we get to see in this original data, we get to see that essentially 2 of the 4 arms from the 4-arm study. And you can view that as a consistency assumption, and it was noted by Matt that this can actually be tested in the 6-arm trial. So the question here that I'm going to ask is, okay, so given the data from 1, the original study, we obviously can identify the results from 3. So given the original data where we assign people to X equals 1 or X equals 0, we can work out what we would see in the putative study where people get N equals 1 and O equals 1, or where people get N equals 0 and O equals 0. But the interesting question is, under what assumptions could we also identify the arms where N is equal to 1 and O is equal to 0, or N is equal to 0 and O is equal to 1? And in the circumstance where we can do that, where we can identify these sort of arms where n and o take different values from the original data, we'll say that the effects of n and o on m and y are separable when that identification holds. So here are two conditions. So the two conditions are, so here I've got y of, I'm thinking about intervening on n and o, and I'm looking at the conditional distribution of y given m. And this first condition says that if I intervene on n and o, then the distribution of y given m does not depend on the value assigned to n. So we've got the left and the right-hand side here are the same, except that on the left we've got n equals 1, and on the right we've got n equals 0. The second condition says that in a world where I intervene on n and o, the value to which I fix o does not change the distribution of m. So if these two conditions hold, then we can identify the two additional arms where n and o take different values. And the proof of this, I'm running out of time here, so I won't go through it, but the proof essentially is close to trivial. Basically, we essentially just take this joint distribution, we rewrite it as the conditional times the marginal, and then we use condition 3 to then switch from x to x tilde in the first term, and switch from n equals x to n equals x tilde in the first term, and we use the second condition to switch from n equals x, from o equals x tilde to o equals x in the second term. And then now both of these pieces are pieces that we would get from our two-arm trial. Okay, and this formula, the formula that we get, if you look at this may look very familiar to people that are familiar with Pearl's mediation formula, and indeed, as a corollary, we get that if I'm interested in the marginal over y when I set n to x and o to x tilde, then that just exactly is given by summing over m. So this is Pearl's mediation formula, which he proposed to identify pure, or also called by him, the natural direct effects. Okay, so let me just tie this back into SWIGs. Those two assumptions that I described can be represented on the SWIG. So here, the first assumption was the conditional distribution of y of n o given m of n o does not depend on n. That's the d-separation we can read off from here. The second one was the m of n o does not depend on o. That's an assumption that I can read off from here, from d-separation. So we can read off those two assumptions from the SWIG. And if there's an unmeasured confounder between m and y, then this first assumption is going to fail, because n would be deconnected to y of n o, because we go n to m of n o and then up to this unmeasured confounder and down to here. Okay, and these conditions, I should also say, would also follow from a non-parametric structural equation model with individual level no direct effect assumptions. Okay, so the key point here is that I've got an identification result for those two cross arms, but this identification could in principle be tested by carrying out a four-arm study. Okay, I think I don't have time to contrast with other mediation approaches, so I'm just going to wrap up here and say there's related work by Vanessa Dideley, Martinson and Stensrud, and a lot of other papers by Matt on this framework, and is also connected to the organic mediation approach of Judith Locke. The summary was that given components NO of treatment, we can formulate these direct and indirect effect contrasts. We had to make assumptions that N only affects the mediator, O only affects the final outcome. The approach requires that these counterfactuals M of NO and Y of NO be well defined. So you have to tell me how you're intervening on N and O. But this approach doesn't require that I have well-defined interventions on the mediator. And we gave conditions under which we could identify all four arms, but those conditions are empirically testable given data from a subsequent four-arm trial in which N and O are both randomized. Thank you. Apologies for running over.
Great, thanks, Thomas. Yeah, so Jamie has been valiantly answering questions in the Q&A, but maybe we will first switch to the discussion by Matt, so he has enough time, and then we can answer some more questions, if that's okay with everyone. All right, perfect. So, Matt, feel free to take it away.
Thank you very much. I hope you hear me well, otherwise shoot out. You see my screen, and it's a pleasure to comment on this work and to comment on the work of such a deep and creative thinker as Thomas and his co-authors. My plan for the next 10 minutes is to give try to give a down-to-earth and subjective summary of what Thomas have said, and then illustrate some of the things, which is just, of course, a little subset of the things in this long and insightful paper with examples, and suggest some future opportunities. So let's start with part one of Thomas's talk on SWIGs, and that's what I would focus on the most too. So Thomas made a nice image in the beginning here and said that the SWIG framework connects the causal graphania with a potential outcome land. And this is really a key intellectual contribution of this work that unifies these two ostensibly different ontologies, which are frameworks that actually may coincide in a lot of cases. And the useful thing of this is, of course, that now, by using SWIGs as a causal graph, we have a common language that we can communicate with. And the fact that we have a common language is useful for us, as many of us consider ourselves at least to be people knowledgeable in causal inference. Then we can communicate with others and use our favorite tool, whether that's writing down conditional independencies or looking at graphs. But another important thing, at least for people who likes to communicate with both theorists, but also with applied researchers, is that the applied researchers, and this is a subjective view, but they seem to like the graphs. They're easier to handle, they're less math heavy, and they could still communicate a lot of their arguments. This is important. And why is this important? Because one of the big legacies of causal inference is that causal inference is grounded in some kind of reality. Our legacy is often that we claim to answer important questions or have make methods that can answer important questions about society today or society in the future. It's not just a math game. So we're not just playing a math game with the new tools, call them graphs or counterfactual variables or potential outcomes. It's more than that. And therefore we want our theory to map to something that people actually care about outside of our community. And one of the key things with the SWIG here that's very easy to conceive and very easy to just realize by looking at the graphs and the way they're constructed is that those assumptions that you encode in the SWIG, at least in the population level SWIG, so that's a subtle difference that Thomas alluded to several times, the differences between population level SWIGs and individual levels ones. We can see if we can get back to them, but these assumptions are in principle falsifiable. Unlike, say, the crossroad assumption that appeared in the mediation literature before for this a lot. Okay, so let me just try to be very concrete and give a couple of examples. So I think one nice example where SWIGs are very useful. I'm not saying that people couldn't identify counterfactual outcomes under time-varying dynamic regimes before the SWIG, because we have papers. Jamie wrote about this in 1986. But the SWIGs make this easier for us to understand, and it makes it easier for us to draw what kind of assumptions we need to impose, and it makes it easier for those who are experts in the field to actually evaluate these kind of assumptions. Okay, so this is the key contribution. We'll try to get into that. I'm not going to draw these heavy graphs right now because that will take us too much time to depict, but let's also consider another thing about SWIG that's nice, and that is that we can encode so-called context-specific independencies and certain context-specific no direct effect assumptions. So the references here I give to you so you can look at them later. That's been considered in some earlier papers, and also in the paper Thomas discussed part of today, so this 2020 paper. Let me try to come up with a different story now. So let's consider a simple vaccine trial. I'm randomly assigning a treatment A. Suppose it's a coronavirus vaccine or a control. You can forget about these covariates, but there exists some covariates that we may or may not measure. Doesn't matter. Just want to make a point about that. And let E be being exposed to the infectious agent. So actually being exposed to the coronavirus. So exposure is not treatment, but exposure to the virus. And Y is some outcome of interest, say severe infection. Okay. And I use superscript to denote counterfactual outcomes. Thomas used parentheses. Now we save a bit of notation, but whatever, it's just the same thing. And let me just go through how we build up a SWIG here. So I decided to put this exposure in the graph. And if I now say you that this is a blinded RCT, I will say that the graph in B is describing my setting of interest, because I don't think the treatment when blinded would affect my behavior and therefore my risk of being exposed to the coronavirus. On the other hand, the treatment A can affect the outcome. So the risk of getting severe infection or being dead for that matter. And that so it's true for some other covariates, okay? And if I want to draw the SWIG here, I'm just encoding that I want to look at the effect of this treatment A. So what happens if I fix A? And this is not a SWIG, but as Thomas said, it's a graph valued function. It's a SWIG template. It is a function of this little variable A here that could be different depending on whether it's treatment or control. Okay. So this is now I draw a simple SWIG for the simple case where you randomly assign the treatment. Now I want to go one step further. And I want to talk about these context-dependent no direct effect assumptions or independent. So here I've instantiated, I've done an additional assumption. So this can be conceived as a so-called challenge trial that people do or want to do, but there are sort of big ethical concerns about that, where people are exposed to the virus. And then you look at the effect of the treatment, so A equals 0 and 1, among those who are exposed. Okay, sounds cool. Okay, so now let me show you another graph where now I say I make another intervention where I force you not to become exposed to the virus. And what do we see in that case? Well, if you're not exposed to the virus, the vaccine does not have any effect on you, okay? Because the vaccine should only work on the virus. So then I remove the effect from little a to y, okay? So why does this matter? I mean, I don't think that these things are used a lot, but I think the SWIGs allow us to encode these kind of assumptions in a nice way. Because now, using this graph, where grantedly I've made 2 interventions, based on the assumptions encoded in these graphs, remember if I go back, this is the DAG of the setting of interest, where I can't really differentiate between these 2 settings. But when I draw the SWIG, I can actually encode the fact that this arrow is absent when you're not exposed. So this means that in this SWIG, I've actually encoded a particular type of interaction. And it's often said that causal graphs cannot encode interactions, but in this case I have. I've really said that when I intervene on E and A, the effect of A really matters depending on the value of E. So this is a kind of a non-parametric way of describing a particular kind of interaction in causal SWIGs that I would say is not equal to do in causal DAGs. And this, of course, also matters for identification. So by using these independencies, which encodes more information than I had in this original DAG, I can now get a new identification formula. Here, I'm not showing you the proof, it's a simple one, for the counterfactual outcome under only treatment little a. So in that case, you could say that doesn't matter. The first thing here is easy to identify and compute non-parametrically from the data. But you'll see that this alternative identification formula may, in some settings, and in more involved settings, I haven't discussed them here now, but maybe in the future, these kind of representations can be important, or at least help us with efficiency, which seems to be a thing statisticians care a lot about. So this was, again, just a simple illustration to make a point. I used interventions on both A and E in my example here, whereas my estimate only depended on the interventions on A. The point is that, for example, if I did a particular trial where, and this is, I'm not saying that this is very common to do, but I made this example simple just to convey a point. In some studies, ethicists argue that the probability of getting no treatment should be small, because there should be an advantage to being in the trial. If they have a prior that the effect of the treatment is large, that probability of being treated should not be 0.5. Then this alternative identification formula could in principle increase the power quite a lot, because you see in one of these terms here, A does not appear. So we could use the whole sample among those who are unexposed in order to compute this particular term. So what I'm trying to say here is that by using SWIGs in this kind of alternative way and encoding our assumptions cleverly, we may even gain efficiency when we design estimators in the future. And that could be, for example, related to this recent JASA publication by Lin Lu, Jamie, Andrea, and Sachs Sean, where they claim with a no direct effect assumptions in a particular applied example that they could increase the efficiency something like 50 times. Okay, But now I'm doing that in a context-specific manner. That may perhaps be interesting. So this was just to show some of the strength of the SWIG and how that can make us argue or reason in perhaps more creative ways. Let's go to the mediation, and I'll be quick because I know I'm running out of time too, but I think I will make a brief point there. And I want us to take one step back and get back to earth when we study mediation, okay? And what do I mean by that? I want, when I study mediation, that's a very mechanistic thing. It's motivated by some subject matter argument, usually. They have some reason why they're interested in this mediation effect. And then I think these causal estimates they're studying, they should also correspond to practically interesting and relevant questions. And the good thing about the interventional mediation analysis that Jamie and Thomas first described in 2010, and me and others have followed up on several times after that, is that we need to be very explicit about why we are doing this analysis, why we are defining these estimates. And Thomas said in the talk another time that this is a feature and not a bug. And I think that's important to reiterate to people, is that we're not doing this abstract mediation game without a reason. And we need to be explicit about this reason when we formulate our estimate. And by doing that, in terms of the treatment decompositions, we also clarify whether or not, or we have to be explicit and transparent about whether this is important for some kind of practical question. And it's also a good exercise for us. That's also something Thomas and Jamie has written in their papers, because it really helps us and forces us to think about how this could be useful, say, for future treatment or future interventions. And Thomas said that, and I want to reiterate that and make it clear, is that unlike the natural direct effects or control direct effects, no interventions on the mediator are required in order for these effects to be well defined. And the last claim I will make, and I made some slides in the appendix that you can look at if you want to, is that arguably many methodologies and applied researchers, when they do mediation analysis, say with natural effects, or they sometimes do, not every time, but sometimes when they argue for principal stratum effects or other estimates in survival analysis, they seem to be alluding to interventionist or separable effects, like Thomas suggested in Pearl's example on smoking, and there are also several other ones I've put in an appendix here, and they're also in the articles. I want to stop there and ask if Thomas any comments. This work is not only rigorously mathematical, but it's also quite philosophical. And this is a philosophical question because this is a philosophical paper, and it may be a bit on the side of a lot of the other derivations there, but Thomas emphasized a lot that he uses population level SWIGs and not necessarily individual level no direct effect assumptions and exclusion restrictions. But when you make stories, for example, in the example in your 2020 or 2021 paper with Jamie and Elia, say in the example on river blindness, determinisms are used a lot. And wouldn't you say that determinisms are a special case of individual level no direct effect assumptions? In which case, I'm not saying that your population level SWIG is contradicting that at all. It just seems like in order for argue for these population level no direct effect assumptions, you rely often on individual level effect assumptions, and that I know you're aware of. But do you not have any good stories for when the population level independence can hold, but not the individual level one? And do you think it's fruitful at all to think and conceive these the notion of differences in individual level effects?
Great.
Yeah, I think I'll leave it there.
Perfect. So then let's we're over time, but obviously it would be really great to actually have a short discussion between you guys on these questions, and some questions maybe in the Q&A.
So can I just, can you hear me?
Yeah.
So just going back to that, the comment there, I wanted to say, yes, I think this is a very reasonable point to say that it's true that often when we're arguing for a particular graph, it is we are arguing in terms of the absence of individual level effects. but in a certain sense, I think our goal was to just clarify exactly what's necessary, what are the assumptions that are required. And there are situations where I think one example is the effect of treatment on the double treated, that there are instances where if you assume the absence of effects at an individual level, then there are quantities that become identified that are not identified if you're just assuming the absence of effects at a population level. And I mean, in a certain sense, I wanted to make this comment here that this isn't the first proposal that there has been to connect these two worlds. There have been there's a pretty well established approach that was referred to in the discussion via twin networks and via non-parametric structural equation models with independent areas. And the point is that in order to do that approach, there are a lot of things that are at least typically taken as standard in that approach. So independence of areas is one. The absence of edges is always the absence of effects at the individual level. Typically, you can intervene on everything. And so, I was trying to think about a way of relating this. That one of the things I think is great about one of our goals in this unification is that, as we all know, different languages have different strengths and weaknesses for expressing certain ideas. That example I came up with is, that whatever it is they say, Italian is the language of music, English the language of air traffic controllers, right? Yeah. And so there are different languages that are suited for different things, and there are notions that are much easier to express in terms of graphs. There are other notions that are much easier to express in terms of potential outcomes. It's true that both can be non-parametric structural equation model is a way of combining these two, but I was in trying to think of the right analogy. In some sense, that seems to me a little bit like saying, well, there's a lot of Latin words in English and there's a lot of Latin words in Italian. So we can, if we just all speak in Latin, then, we'll solve the problem. And that's fine as long as the concepts you want you're working with are things that can be expressed easily in Latin. That's true. And, with non-parametric structural equation models, there are settings, like electric circuits and other things where perhaps you don't need to make the distinction between population level no direct effect and individual level no direct effect. But there are literatures where people worry about that a lot, where they talk about stochastic exclusion rather than individual level exclusion. And so we don't want to throw out that nuance. But I agree with you, it's a philosophical question. And in a certain sense, the thing which makes SWIGs hard is that we wanted to also, that the absence of confounding in the SWIG is carefully set up to just mean the absence of confounding. We're not assuming no cross-world assumptions. So we wanted that to be sort of in principle falsifiable, and that's analogous. Analogously, we wanted to have a no direct effect assumption that was also in principle falsifiable, because a randomized experiment can't tell you that there's no direct effect at the individual level. But certainly there are lots of situations where background knowledge tells you there's no direct effect at the individual level. I don't know if Jamie wants to add anything there.
I'm going to read you a question from Vanessa, and then I have another meeting I have to go to, so I'm going to sign off and leave you to answer it. Maybe because it's too hard. One of the first reactions I always get when talking about separable treatments and separable effects is that this must be a violation of the consistency assumption. An intervention in treatment appears not well defined if it has multiple components. Could you state your view on that? I would say the only thing you could take it from here, Tom, is that there's a certain sense, so people do smoke cigarettes. So I guess that's the multiple current cigarettes, but of any given time do have nicotine and other things. The question, which is something to do, Ryan Andrews asked, is it meaningful to talk about what would have happened if you in the future do a trial where you split them into nicotine and other quantities and what's the relationship of that to current cigarettes, I would say, something like that. Okay, whatever you think that meant, I'm leaving because I have a meeting with a student. I can't.
Okay.
Okay.
All right, thanks. Okay, so in terms of the consistency assumption, I mean, it seems to me this is just an elaboration of the notion of treatment, that instead of having, that if I said to you, well, so yes, there is obviously an assumption that getting both components is the same thing as getting getting both nicotine and the other aspects is the same thing as smoking. But I mean, one point was that Mats has made is, well, that could be tested if you're worried about that. You can do a 6-arm trial where some people get smoked, some people don't smoke, and then the other people are getting these being assigned to these 4 different arms, and we can then compare the outcomes. So in a certain sense, I mean, there's always a tension with the consistency assumption about is consistency an assumption, or is it an axiomatic property? And I guess, yeah, so there is an element in which we're supposing that, in some sense, we're supposing that what it is to smoke is to have those 2 components. But so conceptually, we're supposing that the treatment has these 2 components and they can be decomposed. So with Ryan's question, Ryan's question gets directly to a sort of philosophical question about whether or not you can really observe what's happening before. I guess there are two parts to Ryan's question. It's about, can you observe the natural value and then observe what happens after an intervention? And I think there's 2 parts to that. One, again, there's background knowledge you can use in certain situations. There are lots of trials where, for example, people indicate that they would like to participate in a program, but then maybe the places on the program are there's a shortage of places in the program, and so people are randomly selected to then participate. So there are trials where, of course, you'll need to make additional assumptions in order to get that to be identifying this. But there are trials that I think come quite close to seeing the natural value and then seeing what happens under an intervention. Jamie and I also more recently looked at, there is a literature now about doing brain scans of people where you can see a person's brain arriving at a decision before the person is consciously aware that they've arrived at the decision. So there are these experiments where they put you in the scanner and then you're asked to choose left or right. And then essentially the system knows you're going to choose left before you're consciously aware that you're going to choose left. So they can actually sort of, you're supposed to press one side of the screen, but then they make that side of the screen disappear before, just as you're reaching to press it. And so there is a whole philosophical question about whether or not you could actually anticipate what someone was consciously going to decide before they themselves were consciously aware that they were going to decide. So philosophically, I think that does provide a route where, in principle, you could do this. But I don't know whether that's maybe it probably is a little more context specific, and I realize we are some way over time, so I won't say a lot more.
Yeah. So thanks, Thomas. So okay, great. So let's wrap up today. Just 1 second.
Okay, can I just say one other very quick thing I wanted to comment I wanted to make. People have sometimes said they like SWIGs, but they find it too hard to generate these pictures in LaTeX. And so there is now a package on CTAN, on the Comprehensive Text Archive, that lets you quite easily create SWIGs. So if you're interested, you can do it in LaTeX.
Okay, great. Thanks again, Thomas. And thank you to Mats also for a nice discussion, and to Jamie for answering all the questions. And thank you all for being here. Sorry we went quite a bit over time today. All right, so next week we have a talk by Jan Spies from Stanford on improving inference from simple instruments through compliance estimation. And I hope you all join us then for Jan's talk. Thank you all and have a great day or night.
Thank you.